Alrighty, howdy folks. So let's continue with graphs, trigonometric graphs. In the last lecture, we looked at how to draw the graph of a sine, and also we talked about how to draw, how to draw the graphs of linearly transformed graphs of sine, right? Now let's look at a few more properties of these sine curves. For example, amplitude, period, and shift. These are some of the important components of a sine graph. In fact, of all the trig graphs. So let's look at that. So here is the idea. Consider the graph of the first problem we just worked out. We looked at y equals 3 times sine of 2x minus pi fourths minus 1, right? And we said we can do that based on y equals sine x graph and applying the transformation that we did, x old, y old, and all that stuff. Okay, so I have the green one is the transformed graph. Now, for such a sine function, there's something called amplitude. Amplitude A is half the vertical distance from its trough to peak. Ooh. A sine graph, apparently amplitude A is half the vertical distance from its trough to peak. Trough meaning the peak. Okay. Trough is the bottommost point. Okay, the minimum point, and the maximum y value is the peak. So peak and trough. So now what we are supposed to do is measure the vertical distance from the peak to the trough, and that would be twice the amplitude of a sine curve. Cool. Now if we do that, thus for y equals sine x, what do we have? 2a. Can you tell what 2a would be? This is 1 and this is negative 1. So 1 minus negative 1, that's how we figure out the vertical distance. What's the y value here? Minus the y value here. 1 minus negative 1, and that's going to be 2. So 2 times the amplitude is 2 for a y equals sine x graph, which means a equals 1. So the amplitude A for a sine curve, sine x, y equals sine x, is 1. Cool? Simple calculation. All right. What about for y equals 3 times sine of 2x minus pi fourths minus 1? The idea is still the same. The distance, the vertical distance from the peak to the trough. Okay, the peak, the y value is 2, and at the trough, the y value is negative 4. So we say 2a equals 2 minus negative 4, and that's going to be 6. And then if 2a is 6, a is 3, 6 over 2. Right, 2a is 6, then a is 6 over 2, divide both sides by 2. And one more thing that we can observe here is when we have y equals sine x, we basically are saying 1 sine x, right? And for that, what did the amplitude turn out to be? A was 1. Okay. And for y equals 3 times sine of 2x minus pi fourths minus 1, what did the a turn out to be? The amplitude A turned out to be 3. Is that a coincidence? The answer is no. It's not a coincidence. That is what would happen. It is indeed the case that amplitude of a sine of bx plus c plus d is absolute value of a. Why do we have to do absolute value of a? Because it's entirely possible that we have a negative, maybe I should go back to the previous one. Yeah, let's look at this one. What's the amplitude for this graph? Negative 2 sine of 3x. Again, let's do the peak minus trough y values. 1 minus negative 3 is 4. Divide that by 2, you get 2. So the amplitude for this graph is 2. But A is negative 2. 2, negative 2. Oh, as long as you take the absolute value of A, that's the amplitude. So that's what we are trying to say here. Okay. What was that? Indeed, the case that amplitude of A sine of bx plus c plus d is absolute value of A. Cool? Are you cool with how to calculate the amplitude of a sine curve, of a sine function? Good. And then there are two more things. The period of a sine function and the horizontal shift of a sine curve. So the period of y equals a sine of bx plus c plus d is 2 pi over b. Okay, 2 pi over b. And the horizontal shift is actually negative c over b. Cool. All right. Let's use those two things. What do you think the period for y equals sine of x ought to be? This one says the period would be 2 pi over b. Do we know what b is here? Yeah, b is just 1. What is c? C is 0. Would you agree? When we have y equals sine x and you compare that to a sine bx plus d, c plus d, then a is 1, b is 1, c is 0, d is 0. Do you agree with that? I think I said it too quickly. Would you agree a is 1? B is also 1. We have bx and we have 1x. Plus c. There's nothing being added, so c is 0. The whole thing, we should add a d. We are not adding anything to it, so d must be 0. All right. So, more importantly, b happens to be 1. So the period must be 2 pi over 1. Right? So 2 pi over period is 2 pi over b, which is 2 pi over 1, which is equal to 2 pi. Wait a minute. Didn't we talk about this a long time back? In the previous lecture, we said, hey, the period of a periodic function is such that if f of t plus p is equal to f of t for all t, then that is said to have a period of p. We defined something like that. And at that time we said, oh, the sine x has a period, the y equals sine x graph has a period of 2 pi. And sure enough, we have confirmed that here. So y equals sine x is a period of 2 pi. And what about a horizontal shift? Apparently, horizontal shift is negative c over b, but c happens to be 0. So negative 0 is 0. 0 over 1 is 0. So there is no horizontal shift in this case. Whatever we have as a sine x graph, that's it. No movement either to the left or to the right. On the other hand, okay, and let's see. Is that in fact true? This is the sine x graph, right? Let's check. Does it have a period of 2 pi? 0 to 2 pi, and then the pattern repeats. Yep, so that is in fact true, that it has a sine x has a period of 2 pi, and the shift is 0. The original sine graph, it has not shifted to the right or to the left like we were talking about. Okay, that is true. Good. Then let's look at y equals 3 times sine of 2x minus 4 minus pi over 4 minus 1, that graph. That's the graph that's been drawn here. For this, let's calculate the period and the horizontal shift. First, a is 3, b is 2, c is negative pi 4, d is negative 1. You agree with that? Cool. Now, period is 2 pi over b, and that's 2 pi over 2, which is pi. So this graph, the green one, has a period of pi. Is that true? Okay, let's see. The pattern repeats. This green thing just keeps repeating here. So what is the horizontal distance here? This end is at pi over 8 and that end is at 9 pi over 8. So what's the horizontal distance? Subtract. 9 pi over 8 minus pi over 8 is 8 pi over 8, which is pi. 9 pi over 8 minus 8 pi over minus pi over 8 is 8 pi over 8, which is pi. Sure enough, period is pi. Right? Okay, what about the horizontal shift? C over B. C happens to be negative pi fourths, negative C over B, so negative of negative pi fourths over 2, and the horizontal shift is pi over 8. Right? Now, what does that indicate? What do we mean by horizontal shift? The horizontal shift is, this is the idea. Had we not had this minus pi fourths, this graph, the green one, would have started here at x equal to 0. But because we have a minus pi fourths, the whole graph would be shifted by pi over 8. And sure enough, what was supposed to be at x equal to 0 has scooted to the right. By how much? By pi 8, which is precisely what we are saying horizontal shift. In fact, it's not just the point A that has been shifted, the whole graph has been shifted to the right by an amount equal to pi over 8. Every point on the graph has been shifted by an amount equal to pi over 8. As a result of that, C being negative pi over 4 and this A and this B being equal to 2. Cool. So this is how you can figure out period and horizontal shift. We also talked about how to find the amplitude. Okay. How about this for y equals negative 2 sine of, what do we have? A equals negative 2, B is 3, C is pi half, D equals 1, right? And period would be 2 pi over B, that is 2 pi over 3. And horizontal shift is negative pi over 6, turns out to be. And let's see, the period 2 pi over 3, is that true? How do we figure whether or not the period is 2 pi over 3? Look at the horizontal distance. This is just, the whole thing is drawn for one period and the parent repeats. So the rightmost point is at an x value of 3 pi over 6 and this is at an x value of negative pi over 6. So 3 pi over 6 minus negative pi over 6 becomes 3 pi over 6 plus pi over 6, which is 4 pi over 6 or 2 pi thirds. Right? So, yep, confirmed. Now, how about horizontal shift? That turns out to be negative pi over 6. That indicates that our graph is originally what was at x equal to 0, this point, has been shifted to the left by pi over 6. And in fact, every point has been shifted, the whole curve has been shifted to the left by an amount equal to pi over 6. That's the negative indicates shift to the left. When what, okay, I better be careful here. Notice C happens to be positive, but the horizontal shift is to the left. That's the key to understand. When we say A sine bx plus C plus D, if C is positive, the shift, horizontal shift, is actually to the left. However, horizontal shift, when you calculate, turns out to be negative pi over 6, and that negative value indicates a shift to the left. Okay, all right. What else? Now let's finally look at the effect of those constants A, B, C, and D. So this is something that you are quite familiar with, because I know you know these things were drilled into your heads in high school. Shift, stretches, squishing, and all sorts of stuff. So let's look at that. Recall that if x old, y old is a point and y equals f effect, then the corresponding x new, y new on y equals this is such that x new is this, right? This is something that I talked about before. Okay, now let's focus on this guy. X new is x old minus c over b. From that expression, we can take away a whole lot of important things. One, x new, that is an indication of what changes have happened in the x direction. That means x direction is the horizontal direction. So what was x old and now what is x new? And x new says, how much change has happened in the x direction. Okay, now this change depends only on the constants b and c. Is that true? How do I know that? The change in the x direction, horizontal direction, is dependent only on b and c. I'm making a statement like that. Where did I get that idea from? If you said that comes from this, you're absolutely right. Notice this expression for x new doesn't have any a or d in it. The terms a and d do not appear here at all. So that means only c and b affect the changes in the x direction. Constants a and d do not have any effect on the change in x direction. Okay, what else? Since the constant b lies in the denominator, meaning denominator means we are dividing by something, right? What happens if we divide by something? Its effect is to make things smaller, right? Its effect is to shrink. And in parentheses, I'm saying or stretch. Really? When you divide, aren't you making things smaller? If I have 10, maybe I'll pick 12. If I have 12 and I divide that by 2, 12 becomes 6. And if I divide by 3, 12 becomes 4. If I divide by 4, 12 becomes 3. Right? What am I talking about? So that is actually shrinking. Then what in the world am I talking about? It stretches. Don't fall into the trap. What if I had 12, but I divided that by 1/2? Oh, 12 divided by 1/2 is actually 24. So that has actually stretched. So what did this shrinking or stretching depend on when we divide by b? It depends on whether b is greater than 1 or between 0 and 1, a fraction, right? So the graph does stretch in the horizontal direction if b happens to be between 0 and 1, a fraction. So I'm going to make those statements here. That is, if b is greater than 1, the graph is shrunk horizontally. Okay? It gets squished. And take a look at the graphs. This green one is the graph of y equals sine x. Now using GeoGebra, I plotted on the same one y equals sine of 2x. So that means b is 2 greater than 1. And clearly this has been, the green graph has been shrunk into 1/2 its size, right? Dividing by 2 is making it 1/2. Okay, on the other hand, if 0 less than b less than 1, that is b lies between 0 and 1, this is a fancy way of mathematicians saying a positive fraction between 0 and 1. Cool? And what happens in that case? Well, originally I had this green graph of y equals sine x, and then I plotted y equals sine of 1/2 x. So this is tantamount to dividing by 1/2. Dividing by 1/2 is multiplying by 2. Sure enough, this has stretched to twice the size. horizontally. 0 to 2 pi actually now goes from 0 to 4 pi. Over here, 0 to 2 pi has shrunk to 0 to pi. Cool? And what else? From if b is less than 0, what is the effect of b being less than 0? Let's see. Let's say c is just 0, for simplicity. So what is x new? X old divided by b, right? Now, can you guess as to what would happen if b were to be negative? Let's say -1. X old divided by -1. X old divided by -1 is negative x old. X new, apparently, the new value of x would be negative of the x old. Can you imagine what that would do? If x old is 5, apparently x new would be -5. If x old was 4, the x new would be -4. On the other hand, if x old were to be -2, x new would be +2. So what exactly is happening here? There is a reflection about the y-axis. Would you agree with that? 5 becoming -5. So how would that happen? You take this 5, some 5 somewhere over here, reflect that about y-axis, and you get -5. 4 becomes -4 when reflected. -2 becomes +2 when reflected about y. So that is the effect of a negative value for b. And of course, that is in addition to that reflection. If b were to be, say, -2, again the shrinking and all that would happen. So for instance, I have shown you the graph here. Y equals sine x. Y equals sine of -2x not only is reflected about the y-axis, but because that value is 2, it got shrunk by 2 times. So 0 to 2 pi became 0 to -pi, or -pi to 0. Right? That's the idea. So now my hope is that this has given you a clear understanding of what exactly happens when we apply these shifts, transformations. Why teachers back in high school would say, all right, when you have f of 2x, then the 2 would shrink. Why would it do that? Here is the reason. So there is a much better, clearer understanding of the whole process. Let's move on. Okay. So we looked at the effect of B. Now let's study the effect of C. What does C do? C affects, of course, the x, the horizontal. Its effect is to shift the x coordinate by absolute value of C. Okay. To the left or to the right, we'll figure that out in just a second. But when you have C, the effect of C is to shift to the left or to the right. By how much? By whatever that amount, by whatever that absolute value of that C is. That is, if C is greater than 0, the graph is shifted to the left. Really? Can you see why that would be? If C is greater than 0, the graph is actually shifted to the left. Yeah, it would. Take a look at this. Suppose C is 2. Cool. And x old is 5. B, let us say, is just 1. So that we just have x new equals x old minus C. Ignore the B. So what did I say? C is 2, x old is 5. What is x new? 5 minus 2 became 3. So 5 became 3. Okay, if x old is 4, 4 minus 2, 4 became 2. 5 became 3, 4 became 2, 7 becomes 5. So the new x is basically to the left of the old x. Wouldn't you say that that means actually the x, it has shifted in the x direction to the left? 7 becoming 5, that is a shift to the left by 2 units. 5 becoming 3, that's a shift to the left by 2 units. So basically, ladies and gentlemen, what would this do if b were to be 1? Since the constant it's a factor. Maybe I should, yeah. It's actually shifted by c over b. Yeah, what I said was true only if b were to be 1. So let me change that to c over b. Okay. And also it depends on b, right? If b is negative or positive. So let's assume that b is greater than 0. Okay. Yeah, see, quite conveniently in all my examples, I'm making b to be 1. Okay, so y equals sine x is the green one. And if I look at sine of x plus pi halves, sure enough, this has scooted to the left by pi half, right? Okay, and if c is less than 0, the graph is shifted to the right. And in this case, sine of x minus pi half, the blue one, is the shifted graph of the green one, shifted to the right. Cool? What else? Okay, now we are going to look at the effect of the y values. So how are the y values affected? Y new indicates a change in the y direction. Would you agree? Just like the x new talked about, x new indicated the change in the x direction, y new indicates a change in the y direction or the vertical direction. And again, we can clearly see that only A and D impact the y. B and C have absolutely no effect on the vertical direction, changes in the vertical direction to the original graph. Since the constant A is a multiple of y old, its effect is to shrink or stretch the y coordinate A times. Does that make sense to you? Constant multiple. This is what I mean by that. Let's say the original y value is y old is 3. Now, because we are multiplying by A, let's say we multiply by 2. 3 becomes 6 now. 2 times 3. So 3 became 6. If we multiplied by 4, 4 times 3 is 12. So 3 became 12. Now, that would indicate a stretch in the y direction. But again, notice how careful I am being. I'm picking for A, as I'm talking about stretching part, I'm saying, oh, if A is 2, A is 3, A is 4, I'm picking values for A that are greater than 1. But what if I pick a fraction? Y old, let us say, is 3, but A is 1/3. Now 1/3 times 3 is 1. So 3 became 1. It actually shrunk, right? Became less. So keeping that in mind, that is, if A is greater than 1, the graph is stretched vertically. And sure enough, take a look at this example. Y equals sine x, y equals 2 sine x. That has definitely stretched it. this y value was 1, that became 2. The 0 got doubled and became what? 0 when doubled remains 0. 0 times 2 is 0. So that any y value that is equal to 0 is not affected at all. But all the other values, for instance, at 3 pi over 2, we have -1. So that gets doubled. So 2 times -1 is -2. So this became -2. Right? We can glean all that information based on this formula. That's the beauty of this. Okay, what else? On the other hand, if a were to be a fraction, the graph is shrunk vertically. The original y equals sine x, the green graph, y equals 1/2 sine x, shrinks everything vertically by 1/2. So a y value of 1 here became y value of 1/2, 0.5. A y value of -1 became y value of -1/2 or -0.5. Cool? All right. If a is less than 0, the graph is reflected about the x-axis and then stretched or shrunk depending on the magnitude of a. So here we have the original y equals sine x. And if you're looking at y equals -1/2 sine x, the negative immediately causes this to flip about the x-axis. And because of the 1/2, it gets shrunk, right? First the flipping, reflection about the x-axis, and then the shrinking because of the 1/2. The negative causes the reflection, 1/2 causes the shrink. See how logical sense all of this makes now? Cool. What else? Let's now look at the effect of D. D is being added. So what's the impact? When you add something, things are moving. Let's say A is 1 for simplicity, so that y new is y old plus D. Then if y old is 1, you add and D is 1, then 1 plus 1 becomes 2. So 1 became 2. If we add 2, 1 plus 2 is 3. So 1 became 3. If we add 3, becomes 4. So that is a shift in the y direction. And so that is, if D is greater than 0, the graph is shifted upward by D units. Sure enough, sine x, and look at the graph of sine x plus 1, shift up, right? This peak was at y equals 1, and now the peak is at y equals 2. This trough was at -1, it becomes -1 plus 1 is 0 now. Cool? All right, if D is less than 0, the graph is shifted down by absolute value of D units. Sine x and sine x minus 1. Okay, what else? One last simple concept. By the way, so let me pause for a half a second. Let's take a look at it. Is this all making sense? I hope it did. So we studied the effect of A, B, C, and D the constants, and my hope is that we got a much better idea of the transformation of graphs. I agree, as applied to just sine graph, but the beauty of this is the same concepts apply even for cosine, tangent, and all that. That's why I just wanted to pay attention to every aspect of just the sine graph first. Let's thoroughly understand what happens to the sine graph. And then we'll apply the same principles to cosine and other things. I'm not going to go over in detail any of those things. I think I don't need to, because you can apply the same concepts to that one. Okay. And the last concept we need is next to last. There's one more thing. Domain and range of y equals sine of x. I'm sure You have been bugged a lot in every course that you took. What's the domain? What's the range? Right? Yeah, that's a very important concept. So what's the domain of y equals sine x? Do you know? Looking at this graph, do you have any idea what the domain of sine should be? What in the world is domain? Domain, please pay attention. Domain is all the set of values for which you can evaluate the function. What is that? Is the set of x values for which the function is actually defined. You can actually evaluate the function. For example, is 0 in the domain? Well, ask yourself a simple question. Can I find sine of 0? Yeah, sine of 0 is 0. Cool, done. 0 is in the domain. Is pi half in the domain? Yeah, sine of pi half is 1. Okay, is 0.1 in the domain? Sine of 0.1. Can I find sine of 0.1? I don't know, man. Well, if you have a calculator, you can plug that in. Or this graph actually tells you that if you want actually sine of 0.1, go to an x value of 0.1 and draw a vertical line, see where it cuts the graph, and that y value is sine of 0.1. Let me repeat that. If you want sine of 0.1, you go to an x value of 0.1, draw a vertical line, see where it cuts the graph, and measure the y value there. That is sine of 0.1. You want sine of pi halves. Draw at x equals pi half, draw a vertical line, see where it cuts the graph, and look at the y value. That's 1. Hey, we knew that. So, is there any value of x at which we cannot actually figure out the value of sine? No, looking at this curve, it appears to be defined everywhere. Of course, we stopped it at some 9 pi halves, but the same pattern continues, right? So the truth is, looking at the graph, we observe that the function f of x equals sine x is defined everywhere. Thus, the domain is R, the real number set. Real number set is a fancy way of saying negative infinity to infinity. Cool? Excuse me. And the range, ooh, I shouldn't have shown that. Cool. What's the range though? Do you remember what range, looking at a graph of a function, we can actually tell what the range is? The range is the set of values of y values going from the smallest y value to the largest y value, and everything in between if it is included. So whatever y values are included, that is your range. Is -1 included in how should I put it? Okay. Is sine of something equal to -1? Yeah, sine of 3 pi halves is -1. So by virtue of x being 3 pi halves, we have a y value of -1. So -1 is included in the range. And is y value of 0 included? Yeah, sine of 0 is 0. So 0 is in the range. 1 in the range? Yes, it is. Is 2 in the range? No. 2 is not in the range, right? Because no matter sine of what value you figure out, it will never be equal to 2. This graph tells you that. Had this been able to be equal to 2, it would have stretched all the way up to a y value of 2. But 2 is not there. Maximum value is 1. Maximum y value is 1. Minimum y value is -1. So the range and everything in between. The important thing is everything in between. So the range happens to be this closed set -1, 1. This what? Closed set. What in the world do I mean by that? Oh, by the way, I have brackets, square brackets here. Could I have just put parentheses? Is that the same? Yeah, brackets, parentheses, what's the difference, man? No, there is a big difference, right? When we say brackets -1, 1, we mean every value between -1 and 1, every y value between -1 and 1 in this case, including -1 and +1. Right? The square brackets tell you that the endpoints are included. Had we made this into a parenthesis, kind of like how we made parenthesis for this -infinity to infinity, it tells you that -infinity itself is not included and infinity itself is not included. So that's what would have happened. Had we had parentheses here, that would have indicated all the y values between -1 and 1, and -1 and 1 themselves are not included had we had parentheses. But -1 is included in this case and +1 is included in this case. That's why we put a bracket. Cool. We need to be aware of this. For all the trig functions, we need to know what the domain and range are. Okay, folks? All right, one last concept. What's the graph of y equals cosine x look like? Well, last time I showed you a point moving in a circle and all that. If we looked at the position, x position of that point, then that follows a cosine curve. Okay, when theta is 0, cosine theta is 1. When theta is pi halves, cosine pi half is 0. So here instead of theta, I'm saying x. Right? So look at the graph of cosine x. It looks very much like a sine graph. The only thing is, at x equal to 0, sine graph was 0. Sine was 0. But at x equal to 0, we have 1. What's the period of a cosine? Let's take a look at the period, which means look at the horizontal distance from peak to peak. A peak is at x equal to 0. And the next peak is at x equals 2 pi. What's the difference? 2 pi. So cosine also has the same period as sine, which is equal to 2 pi. What's the domain? Everywhere. All real numbers. -infinity to infinity. What's the range? -1 to +1. Cool? And so the cosine function is periodic with a period 2 pi, and cosine of t plus 2 pi is cosine of t. As for the graph of y, we can adopt the same procedure as we did for the sine function. Right? I'm not going to go over all of the cosine stuff in detail, but I will expect you to be able to solve problems like this. What is that? Suppose I give you suppose you know this graph of y equals cosine x. It would be perfectly reasonable on my part to say, all right, folks, figure out the graph of y equals 2 cosine 3x minus 1 plus 5. How would you figure that out? The same procedure. That is, you make the table. You pick salient points. That means you pick this point, 0, 1, pi half 0, pi and -1, and 3 pi half 0, 2 pi and 1. So pick those 5 points and transform those 5 points and redraw the graph. So that is the period. That is the one period that you will draw. Cool? That's the idea. Whew. That was a long one. All right, folks. Thank you very much.